Welcome back to an introduction to oceanography from the textbook Essentials of Oceanography, the 8th edition, written by Tom Garrison and Robert Ellis, and from Cengage Learning. Of course, I'm your instructor, Dave Cocchiarella, and today we're talking about the ocean floor. The ocean floor, basically two separate subjects, one being the actual ocean basin, how it was formed, what it looks like, what is the structure of the ocean basin, and why are those structures there. The second part being sediment, and how sediment gets there is only part of the story. The other part of the story is the story that sediment can tell us about the history of the Earth. So let's start with an overview of the main concepts from this lecture. So number one, tectonics shaped the seabed. We've already mentioned that. Tectonic forces, the unifying theory of plate tectonics, explains the shape of the seabed. The ocean floor is divided into two parts, the continental margins and the deep ocean basins. And those continental margins really are just seaward extensions of the continents, and they usually are granitic. They're made of granite. And the deep seabeds are completely different features, and they are made up of basalt, a low silica rock. Continental margins can be active with earthquakes and volcanoes, or passive, depending on local plate movement. The mid-ocean ridge system is perhaps Earth's most prominent feature. It's the world's longest mountain range. Most of the water of the world ocean circulates through the hot oceanic crust in these ridges about every 10 million years. Using remote sensing methods, oceanographers have mapped the world ocean in amazing detail. That's something we'll take a look at. All right, Chapter 3 in review. The Earth's crust is attached to the very uppermost part of the mantle, the rigid part of the mantle, into what are known as lithospheric plates. And what you're looking at here are those lithospheric plates broken down into all the different plates that exist on Earth's surface. We have the large Pacific plate and the North American plate, the South American plate, the African plate, which is composed of part oceanic and continental crust and lithosphere, the Indian Australian plate, the Eurasian plate. All these plates are moving along, they are rigid, and they're moving along on a hot and pliable upper mantle known as the asthenosphere. Some of these plates run into each other and they converge. Oceanic plates can converge. Oceanic and continental plates can converge. Continental plates can both converge. They also diverge, as we see at the mid-ocean or the mid-Atlantic ridge. They move apart, and they also have transform boundaries like we see in the San Andreas Fault. And of course, those convergent boundaries, the Nazca Plate, where the Nazca Plate converges with and subducts under the South American Plate. So here are the basic plate boundaries and some of the different characteristics of those plate boundaries, much of which we have discussed in detail in Chapter 3. And if you need an update on that, I suggest you watch Chapter 3 and get more information on the divergent, convergent, and transform plate boundaries. One of the things that we learn in Chapter 4 is that we know a tremendous amount about the ocean basins by the mapping of ocean basins. And the mapping of ocean basins is the scientific pursuit called bathymetry. Bathymetry is the discovery and the study of ocean floor contours. And early studies often used just a weighted line, and they would just measure the depth to the ocean floor. Big advances came with echo sounding, and then multi-beam echo sounders, and of course finally with satellite altimetry. And we've seen these pictures from Chapter 1, different types of echo sounding, using methods of pinging through the ocean, sending a ping of sound and listening for it to bounce back and getting an idea of just how deep that particular part of the ocean floor is. And this is a very important advancement in understanding what the deep ocean basins look like. Multi-beam echo sounders provide more accurate measurements than just normal echo sounders. They use up to 121 beams to measure the contours of the ocean floor. They also get it done much more quickly. Satellite altimetry, this is kind of amazing. Satellites can measure the sea surface height from orbit, meaning they can see just how high the sea surface is from orbit. And what satellites tell us is that the sea surface isn't flat. Now, you pour a little bit of water out on a table and it creates a completely flat surface. But what we know about the sea is that sea surface is not completely flat. Large pieces of crust, like a seamount, will cause gravitational pull to force water to mound up over on top of it. And we can have a several foot difference between sea heights at the edge of a continent and sea heights in the middle of the ocean. And this is all done through satellite altimetry. So here is South America viewed by satellite, by the satellite altimetry. You can see the high Andes Mountains. You can see the Peru-Chile Trench running the length of the continent on that active west coast. The transform faults and fracture zones in the Chilean rise, that's in the lower left. And you can also see a very large continental shelf on the passive, the trailing edge of the southern part of the continent. So what this tells us is that on the west side of South America, because of that trench, there is a convergent boundary where oceanic lithosphere is subducting under continental lithosphere. But on the east side of, and that makes that an active margin, on the east side of the continent, the continental lithosphere is connected to the oceanic lithosphere. It's acting as one plate moving in the same direction, and we have a passive margin, and there we have a much broader continental shelf. So a cross-section of the Atlantic Basin, we can see this from the cross-section of the Atlantic Basin from C to D, and the cross-section of the United States continent, well, the North American continent from A to B, and you can get an idea of just how big that Atlantic, that mid-ocean ridge is. You can see the Rocky Mountains and the Sierra Mountains. Well, the Atlantic ridge, the mid-Atlantic ridge, that mid-ocean ridge is just about as high as the Rocky Mountains when you do a cross-section. So although ocean depth is definitely greater than the average height of the continent, the general range of the contours are very similar. The general range of the mountain ranges are very similar. So features of Earth's solid surface are shown in percentages of the planet's total surface. So about 10% are mountains, and about 19% are continental lowlands. About 11% of the entire Earth are these continental shelves and slopes, these seaward extensions of the continents. The continental rise, which goes from the shelf down to the deep ocean floor, is only about 4%. And then 30% are ocean basins, about 22% are the ocean ridges, and volcanic island arcs and submarine trenches and volcanoes make up about 4%. So about 70% of the land, or 70% of the globe is ocean, and about 30% is land. All right, now here's a graph showing the distribution of elevations and depths on the Earth. So you have on the bottom of the x-axis the percentage of the Earth's surface, and then on the y-axis your depth in meters and your height above sea level. This is not a land to sea profile of the Earth, but rather a plot of the area of the Earth's surface above any given elevation or depth below sea level. So more than half of the Earth's solid surface is at least 3,000 meters, 10,000 feet below sea level. Almost half of the entire surface is below 3,000 feet below sea level. And the average depth of the ocean is about 3,790 meters, which is much, much greater than the average elevation of the continents. What are the two classifications of the ocean floor? You have the continental margins, which we talked about, which are the submerged outer edge of the continents, and then we have the ocean basins. And the ocean basins are the deep sea floor. So the continental margins are still part of the continental crust. The ocean basins are all oceanic crust. So the continental margins will be made of granite, and the ocean basins made of basalt. So what are the two types of continental margins? What makes up the margin? There are passive margins called Atlantic type margins, and they face the edges of diverging tectonic plates, meaning the Atlantic Ocean, the Atlantic coastline of North America and South America look toward a diverging tectonic plate. There is no convergence going on between the Atlantic and the North America. Very little volcanic or earthquake activity is associated with passive margins. And then active margins, known as Pacific type margins, are located near the edges of converging plates. Active margins are the sites of lots and lots of volcanic and earthquake activity. So continental margins, the margins themselves, the seaward extension of the continent that's underwater, has several components. There is the shelf, which you've probably heard about since you were in grade school, the shallow, submerged edge of the continent. And then there's the slope, and the slope is the transition between the continental shelf and the deep ocean floor. The shelf break is the abrupt transition from the continental shelf to the continental slope. And then The continental rise is an accumulation of sediment found right at the base of that continental slope. And that's basically along passive margins, Atlantic-type margins. So here's a cross-section. So this is the cross-section. And what you're looking at here is a passive margins in a deep ocean basin. So here's your continental margin, and here's your other continental margin. And so the continental shelf is the seaward extension of the continent. And it's generally covered by some type of sediment. And that is the continental shelf that goes way out from our side of the continent. And then the continental slope is where the continental crust ends. And it's a downward motion down toward the ocean. And then you get that continental rise, which is more sediment that's flown out into the ocean. Underneath the continental rise is the oceanic crust. So you have this difference between the continent and the oceanic crust. So here's our oceanic crust here, and that's our continental crust. And the two are sutured together. One's not moving toward the other. And this, all underneath this, is going to be your upper mantle, your asthenosphere. Everything underneath these two long red lines I'm drawing is the upper mantle or the asthenosphere. So this is the continental lithosphere and then the oceanic lithosphere. These are two separate plates, one plate and a second plate. And the plate boundary is right here at the ocean ridge. This is a divergent boundary where those two plates are spreading apart. And again, the structure of the ocean basin, both being passive, is your continental shelf, your continental slope, and that takes you from the shelf down to the oceanic crust. And then the continental rise is where sediment has covered that transition. And we have the same thing happening on the other side of the basin as well. So here we are looking at both an active and a passive margin. So your passive margin is here, your active margin is here. Your active margin is active because it is at a plate boundary. That is a plate boundary where an oceanic lithospheric plate is converging with a continental lithospheric plate. Here it's a passive margin because it looks out toward a divergent plate boundary, which is where two oceanic lithospheric plates are diverging from one another at a mid-ocean ridge, in this case the mid-Atlantic ridge. And here this passive margin is where the oceanic and the continental crust are sutured together and moving along on top of the same lithospheric plate. So this is one plate, and, well, I should say this is one plate, this is your second plate, and over here is your third plate. So why do we have an active margin or a passive margin? So our active margin occurs because it is near this converging plate boundary. Our active margin is where we have a oceanic lithospheric plate subducting under a continental lithospheric plate. We get a trench formation, and this subducting plate creates earthquakes along the subduction zone. And in addition to earthquakes along the subduction zone, the melting of the mantle wedge here creates mantle that bubbles up and eventually creates volcanic mountains along the margin of the continent. So this is an active margin, whereas in the passive margin, there's very little volcanic activity, or no volcanic activity. The only volcanism going on or earthquakes going on is out here at the diverging center. So typical continental margin bordering a tectonically active Pacific type and a passive Atlantic type moving continent. The vertical scale, of course, has been exaggerated. Passive margins are continental margins facing the edges of diverging plates, and active margins are continental margins near the edges of converging plates, or near places where plates are slipping past one another. That can also be tectonically active. So those are your passive and your active margins. Now, here's an interesting cutaway of what's happening on the North American plate, up where the Juan de Fuca, which is a small plate, is subducting underneath the North American plate. And that subduction zone creates earthquakes where it subducts underneath and it basically rubs against, the two plates rub against each other. And then the mantle wedge that melts creates our active volcanoes. So Mount Rainier, Mount Adams, of course, this is where Mount St. Helens occurred as well. So this is a very good example of an active margin, an active continental margin, where a subduction zone is creating a lot of earthquakes and a lot of volcanism, a lot of volcanoes. So I said our continental shelves and our continental margins are really seaward extensions of the continents. Most of the material composing a shelf comes from the erosion of the adjacent continent. So here's our adjacent continent, and most of this material is all some type of sediment. Rivers transport most of the sediment that makes up the continental shelf. The continental slope is a transition between the continental shelf and the deep ocean floor, and turbidity currents are just basically currents of water that are denser because they're full of sediment, transport most of the sediment that makes up the continental rise. And again, this is our continental rise between the continental slope here and the deep ocean floor. So the oceanic crust probably extends to about this point. Everything west of that is going to be continental crust. This is all oceanic crust. And the continental rise literally covers up that transition zone. The continental slope is the transition between the oceanic and the continent, and then the continental shelf is largely covered in sediment as well. One of the things that we know by looking at geology and ice cores and sediment cores is that the climate of the Earth has changed almost continuously over the 4.6 billion years the Earth has been around. This is a graph showing about 250,000 years. And on the far right, that point C is today's sea level. And what this graph is showing us is how sea level has changed, and dramatically at times, over the last 250,000 years. And this data is taken from ocean floor cores, and those ocean floor cores give us a very good idea of the temperature at the time, and knowing the temperature gives us an idea of how much of the ocean water is locked up in the ice during the ice ages. So the rise and fall of sea level is largely due to the coming and going of ice ages, periods of increased and decreased glaciation. Literally, when you have large glaciers during an ice age, tremendous amounts of glaciation over the continents and the oceans, the water is locked up in the ice and the sea level falls. So colder periods create lower sea levels. Point A indicates a low stand about 125 meters at the climax of the last ice age. So the end of the last ice age is right here, is thought to have ended anywhere between 12 and 18,000 years ago. And that was when we were very, very cold. The ice age began to end, and immediately temperatures began to rise, and sea level also began to rise. And the thinking is, based on observations, is sea level continues to rise at this point. Now, B indicates a high stand, 6 meters or so above current sea level during the last time we were interglacial or between glaciation. So this cold period, low sea level, represents glaciation. This cold period, low sea level, represents glaciation. This is the last interglacial. We're currently in an interglacial as well. And that was about 120,000 years ago, the last interglacial. And point C shows the present sea level. So sea level continues to rise as we come out of the last ice age. And because we are entering this period of global warming, it appears as though sea level increases are accelerating as well. All right, a little bit about submarine canyons. They're features of some continental margins. You have to have water coming off the continent to have a submarine canyon. They cut into the continental shelf and slope, and they basically terminate with these deep sea fans out on the deep sea floor. And this avalanche is one of those turbidity currents that I was talking about. This is actually a picture taken just offshore of Jamaica, and there was a submarine in port, or close to port, that was very close to the bottom, and its propellers kicked up enough sand off the bottom, sand and silt and whatever sediment was on the bottom, that it kicked up this big cloud of silt. And because that cloud had more stuff in it, it was denser, that water was denser, and that dense water literally rolled downhill. So An avalanche-like sediment movement caused when turbulence mixes sediments into water above a slope. They're called turbidity currents. The turbidity current flowing down a submerged slope off the island of Jamaica. Here again, the propeller of a submarine causes the turbidity current by disturbing the sediment along that slope. All right, so we've talked a lot about the continental margins, the continental slopes, and the rises, and now we want to talk a little bit about the deep ocean basins. So the features of the deep ocean basins, we talked with plate tectonics about the oceanic ridges. There's also the abyssal plain between the ridge and the continents and abyssal hills. And then in addition to that, there are seamounts and volcanoes and these things called guyots. There's trenches and island arcs, and there's hydrothermal vents. All right, so this is an illustration of all the oceanic ridges, and this is where continents have been spreading apart and oceans have formed as those rift valleys got bigger and bigger and bigger. So this is the Atlantic, mid-Atlantic ridge, and then the Indian ridge, and that crosses over here down into the Pacific Antarctic ridge, and the East Pacific ridge is displaced because there's been almost continuous spreading for almost 225 million years here, and then this East Pacific ridge sort of culminates here where we have some subduction, and then we also have some transform boundaries. And so this is where our spreading ridges are. So an oceanic ridge is a mountainous change of young basaltic rock at an active spreading center of the ocean. If the ocean evaporates, the ridges would be Earth's most prominent feature. Ocean ridges are widest, fastest spreading rates where they're most active, like in the Pacific. So really rapidly spreading in the Pacific, and so that's where they are the biggest. Upwelling of magma from beneath the ocean floor causes the ridges to bulge up. They are often devoid of any sediment because they're the youngest rocks on the ocean floor, and those youngest rocks are always located at the active ridge center. Again, because the Earth is a sphere, we can't have one continuous line of a spreading center. So these spreading centers get split and displaced from one another by these transform faults. The transform faults and these fracture zones along oceanic ridges. Transform faults are the fractures along the lithospheric plates as they slide horizontally past one another. These plates in the fracture zone are moving in the same direction, while the transform fault, they're moving in opposite directions. So it means that these two chunks of the plate are moving in the same direction, and these two chunks of the plate are moving in the same direction, but at this transform fault, the plates are moving in opposite directions. Now, here the plates are moving in opposite directions, and that's a fault. In this location, these plates may be moving in the same direction, but they could also be moving at different rates. And so that's your fracture zone, and that's your transform fault. All right, hydrothermal vents, very, very interesting. They are sites where superheated water containing dissolved minerals and gases escape through fissures or vents. So cool water, shown by the blue arrows, is heated as it descends toward the hot magma chamber. So in this period of this water moving through this rock, it leaches out, or it takes out the sulfur, the iron, the copper, the zinc, and other materials from the rock. Then as that water is heated, it becomes less dense and it bubbles up through the mid-ocean ridge, returning to the surface, carrying those elements upward and discharging them at the hydrothermal springs or the hydrothermal vents. So those hydrothermal vents right here in the center of that mid-ocean ridge are hot springs on active oceanic ridges. So this is the cross-section of the very central part of the mid-ocean ridge. And what you have to remember in this mid-ocean ridge situation is the entire mid-ocean ridge looks something like this. It's a ridge, and then you get the central rift valley. And so the ridge is this very long point across the entire screen here, all right? This section on this illustration from here to here is just being shown right in this section on what I've drawn. So this on the illustration is just this very central section. The ridge is significantly higher than the rest of the sea floor. All right, so a cross-section of the central part of the mid-ocean ridge showing the origin of those hydrothermal vents. water leaches down through the oceanic crust, picking up all those minerals, and where it's superheated, it bubbles back up. And sometimes they call these things black smokers or white smokers, depending on the type of chemicals that come out. But in addition to these hydrothermal vents, this zone is also where any new magma would bubble up and form and create new rock, causing those ocean centers, again, to move away from each other. So this is literally the point of a plate boundary, a diverging plate boundary, right up to the center, of this. And not only do you get these hot smokers, but this is also where you get magma and volcanic activity as well, where that magma flows out, creating lava on the sea floor that solidifies into rock. Some other interesting features on the sea floor are these seamounts and guyots. Seamounts are the volcanic projections from the ocean floor that do not rise above sea level. So a seamount is going to be anything that doesn't quite ever get to sea level. And very likely they are formed at the mid-ocean ridge, and then they are carried away from the mid-ocean ridge as those two oceanic plates diverge. All right, well, if they can get to the surface, much like they did in Iceland, then you have volcanoes above the surface. If they don't get to the surface, they're called a seamount. Where you get a guyot is where you get this volcano that rises above the surface, and then as it begins to move away, it's no longer forming, and the sea surface literally erodes away the top of it, so it becomes flat. And then as it continues to move away, it just becomes this flat-topped seamount. So a seamount is not flat-topped, and a guyot is flat-topped. Abyssal hills are flat areas of sediment-covered ocean floor found between the continental margin and the ocean ridges. Abyssal hills tend to be quite small, extinct volcanoes or rock intrusions near oceanic ridges. Due to the accumulation of sediment, though, abyssal plains, the plains way out here, are very, very flat. Most of the sediment is of terrestrial or shallow water origin, meaning all the sediment that covers the abyssal plains is basically coming off of the continents around the ocean. All right, the other thing that tectonics does is where we have converging plates, whether it's oceanic and oceanic and continental, those two converging plates are going to create trenches. Trenches are arc-shaped depressions in the ocean floor caused by the subduction of converging ocean plates. Trenches and their associated island arcs form in subduction zones. Most trenches are around the edges of the active Pacific, and the trenches in the island arcs are among the most active geologic features on Earth. If you think about all the earthquakes and volcanoes in Japan lately, that's because you have a very significant plate motion here and a significant oceanic trench. Trenches are the deepest places on Earth, and they're between 3 and 6 kilometers deep. The deepest, much deeper than the adjacent basin floor. The ocean's greatest depth is the Marianas Trench. The deepest reaches more than 11,000 or 36,000 feet below sea level, and that's the Mariana Trench right there, and there's the Challenger Deep Trench. So those are the deepest trenches. And literally, this is where two oceanic plates are converging. And when those oceanic plates converge, so here's one, that's the younger and the less dense, and here's the older and the more dense because it's colder. There is the oceanic trench. And with these very fast subduction zones, you get these very deep trenches. And that's where our ocean trenches come from. So there's the Mariana Trench and the Challenger Trench. Actually deeper than Mount Everest is high. And I guess that's the point. About 20% deeper than Mount Everest is high. All right, so that's kind of our look at ocean basins. It was very difficult to discover the shape of the seabed. Using a weight at the end of a rope was not a good method at all. But then with the development of echo sounders and then submersibles and then multiple beam echo sounders, we were able to get a better handle on the shape of the ocean floor. But even today, it's thought that we know more about the contours of Mars than the contours of our own ocean floor. So we know that the seafloor feature results from a combination of tectonic activities and the process of erosion and deposition. So think about that. A lot of what we talked about was a function of plate tectonics creating trenches and ridges. But the reason why the continental shelf or the continental rise exists is because of erosion from the continent and the deposition of that sediment on the ocean floor. And the reason why the abyssal plains are flat is because millions of years of sediment have filtered down and just flattened out on top of the seafloor. So the ocean basin is a combination of tectonic activity and the processes of erosion and deposition. The ocean floor can be divided into two regions: the margins, which are the seaward extensions of the continents, and the deep ocean basins. The continental margin is relatively shallow ocean floor nearest the shore, consists of the continental shelf covered by sediment and the continental slope. And remember, the continental rise is that sediment that connects the slope and the shelf together. Continental margins share the structure of the adjacent continents, but the ocean floor away from the land has a much different origin and history. Prominent features of the deep ocean basin include the oceanic ridges, flat abyssal plains, deep ocean trenches, curving chains of volcanic islands, and it's the processes of plate tectonics, erosion, and sediment deposition that have shaped the continental margins and our basins. All right, first, sediment. What is sediment? Loose accumulations of particulate matter. The depth and the composition of sediment tells us of relatively recent events in the ocean basin above, but very, very deep layers of sediment buried under lots and lots of other material can tell us about what's happened in the distant past. Number two, the most abundant sediments are Terrigenous, that's from land, and then Biogenous, which are from once living creatures, once living organisms in the ocean water column becoming sediment. The volume of Terrigenous sediment exceeds that of Biogenous sediment, but Biogenous material covers a greater area of the seabed. The sediment from land basically covers the continental shelves and the continental rise. The Biogenous sediment is what covers the abyssal plains. Number three, marine sediments have been uplifted and exposed on land. So sediment doesn't just stay on the ocean floor. It's covered by more sediment. Eventually it's compacted and lithified, turned into sedimentary rock. And eventually, due to plate tectonics, that sedimentary rock can be uplifted and exposed on land, much like what we see in Arizona's Grand Canyon. Number four, because marine sediments are usually subducted along with the seabed in which they lie, the oldest sediments are relatively young and rarely any older than about 180 to 200 million years of age. So sediments are oftentimes referred to as the memory of the ocean because sediment tells us what happened in the ocean basin above in the distant past. Sediments are particles of organic and inorganic, so living and non-living matter that accumulate in loose, unconsolidated forms. Now, unconsolidated means it's not compacted and lithified into rock. So sediment is not rock, it's a different thing. Now, sediment becomes sedimentary rock when it is compacted and lithified. And lithified essentially means cementing of unconsolidated materials together. So sediment originates from the weathering and erosion of rocks and the activity of living organisms, also from volcanic eruptions and the chemical processes within water. All of these processes can generate sediment. Sediment is essentially color-based on its origin. The color of the sediment is typically an indication of its origin. Biological sediments are white or cream-colored, and that reflects the shells of biological creatures. Sediments that are high in silica tend to be gray. Deep sea clays can be red due to the oxidation or the rusting of iron within the sediment, but clay can also be anywhere from a tan to a very deep chocolate brown. Sediment that is precipitated from the sea water itself, nodular sediment, is typically a very dark brown or a black. We said that seafloor sediment is the memory of the ocean. As sediment slowly accumulates on the ocean floor, it records local and sometimes global events in the composition of the sediment. Sediment can be classified by the particle size. Sediments can be classified by the size of the individual particles, with most marine sediments being made of finer particles, those small particles such as sand, silt, and the really small stuff, the clays. So streams and currents and waves generally transport smaller particles farther than larger particles. Therefore, sediment is sorted while being transported. Well-sorted sediment, sediment of mostly one size, occurs in environments where the energy fluctuates in narrow limits, typically a low-energy environment. But poorly sorted sediments, sediments of lots of different sizes, will occur in environments where the energy fluctuates greatly, typical in high-energy environments. So what does that all mean? Well, sediment is transported by a medium. That medium is typically going to be water or wind. And the faster the medium is moving, the larger the particles the medium can carry. So a very fast-moving stream may carry along with it sediment in the size of clay, silt, sand, maybe even small pebbles. And a rapidly moving stream might even move larger rocks along the stream bed. Once that stream empties out into the ocean, it's no longer in a narrow stream channel, and the water immediately begins to slow down. As that water slows down, just like if it were with wind, the larger particles will begin to fall out. They can no longer be supported in the medium. Gravity takes over. And as the water continues to move out, in this case out to sea, and slows and slows and slows again, smaller and smaller particles are dropped out of it until all that is left is the finest particles, and those are the ones that tend to settle well away from the continental margins out on the abyssal plain. So if you have a low energy environment, you're basically only going to have sediment of one size, whatever the largest size, that level of that energy of the environment can carry. But if you have a high energy environment like the surf zone, breaking waves and water rushing up and down the coastline or the beaches will allow for there to be lots of different or poorly sorted sediments, sediments of lots of different sizes. So that's the difference between your well-sorted sediment in the low energy environments and your poorly sorted sediment in your high energy environments. And this table just gives you the particle sizes of sediments. And again, the sediments we typically find in the ocean are the smallest sands, silts, and clays. So this chart is going to show us how different sediment sizes are dislodged, carried, and then deposited by streams based on the stream velocity and the size of the particle. So there's a lot of lines there. It's a little on the confusing side, but if we go to point A, what this chart is telling us is that a piece of sand the size of point A is going to need a stream velocity of about 20 centimeters per second to dislodge that sand from the stream bed and to carry it downstream. Once that stream bed velocity falls below about 1 centimeter per second, then it will no longer hold that size piece of sand, and that piece of sand will drop out and be deposited. So it's interesting, if you look at the clays, because of the way clays stick together so well, it takes a very high stream velocity to dislodge them, but it takes a very, very low stream velocity before they'll actually begin to settle out and be deposited on the surface. And of course, gravel, something very large, is going to take a tremendous stream velocity, dislodge it and carry it along. The larger it gets, the more velocity it takes. And very quickly, if that stream velocity begins to fall, then that gravel will be deposited out of the stream flow. Sediment can be classified by its size, it can be classified by its color, but it can also be classified by its source. And the classification of marine sediments by source is broken down into Terrigenous, Biogenous, Hydrogenous, and Cosmogenous. And Terrigenous, with terra being the root of the word, means sediment that comes from land. Erosion off the land, perhaps the debris from volcanic eruptions, or blowing dust. And there's actually a tremendous amount of dust that's blown off of North Africa out into the Atlantic Ocean every year. That makes up a large amount of sediment. Typically, quartz, sands, clays, maybe estuarine mud, and it's dominant on coastal margins, so it's mainly right on those coastal margins, those seaward extensions of the coastline. And then it does get out into the abyssal plains and the polar ocean floors. So the second classification by source is Biogenous, and these are the next most abundant and are composed of calcium shells of silicate skeletons of planktons, mollusks, and corals. So Biogenous is basically the organic accumulation of hard parts of submarine organisms. So Terrigenous is the most abundant, Biogenous is the second most abundant, and you're either going to get these calcium shells or silicate skeletons, and they're going to create these oozes on the bottom of the ocean floor that is just a combination of a little bit of a Terrigenous sediment and then the Biogenous sediment. It makes the dominant on the deep ocean floor, and it creates the ooze. Now, you get deeper and deeper underneath the surface, and that ooze is lithified like other sediment into sedimentary rock. Hydrogenous, the precipitation of dissolved minerals from water, typically done by bacteria, can be manganese nodules or phosphorite or different types of deposits we find literally on the bottom of the ocean floor where dissolved minerals are precipitated. So they've been dissolved, so they're a solid mineral, then they're dissolved into the water, and then once they're part of the solution in the water, then they can be precipitated out of that solution and become solid again. So cosmogenous is dust from space and meteorite debris. So just like dust off of Africa, dust from space enters the atmosphere, falls to Earth, and settles into the ocean. And you get very small proportions of cosmogenous types of sediments on the ocean floor. Where do we get sediment? If we're talking about terrigenous sediment, we get that from the weathering of continental rock. Weathering is the process which acts at the Earth's surface to decompose and break down rocks. There's a couple different types of weathering. You have mechanical or physical weathering and chemical weathering. And mechanical or physical weathering is the breakdown of rock material into smaller and smaller pieces with no change in the chemical composition of the weathered material. That could be from wind, from rain. It could also be from a tree growing into a rock and splitting it into smaller and smaller pieces. Lots of different types of mechanical or physical weathering. Chemical weathering is the breakdown of rocks by chemical agents. Obviously, the chief chemical agent is water, which carries dissociated carbonic acid, meaning acid rain, a little bit of acidity because of carbon dioxide in the water, and that tends to break down rock, particularly sedimentary rock. It breaks it down quite easily. So different types of mechanical weathering. Expansion and contraction. The thermal heating and cooling of rocks causes expansion and contraction, and that can cause them to fracture and break into smaller and smaller pieces. Frost action or frost wedging. Water freezes at night. It expands because it occupies more volume as ice, and that wedges the rocks apart. And then it melts the next day, and then you have a larger opening for more water to run into and freeze and expand that joint again. So basically you have to have a situation where the temperature moves back and forth over the freezing point, and then the freezing and the unfreezing, the freezing and unfreezing of water within a rock will break it into smaller and smaller pieces. Exfoliation is the process in which curved plates of rock are stripped from a larger mass. An example would be Half Dome out in California. Yosemite Valley. You have large emplaced plutons of igneous rock. A pluton is because the rock cooled underground, and as the material above that rock weathers and it's exposed at the surface, there's less and less pressure on that rock, and so it begins to expand upward, and it splits, it shears off, it breaks off in these sheets, and those exfoliation sheets break away, and that's the process of mechanical weathering. You can also get cracking of rocks by plant roots and burrowing animals. There's chemical weathering, which we talked about. Factors which affect the rate of chemical weathering are the particle size. The smaller the size, the greater the surface, and hence more rapid weathering. Composition, the climate, different types of vegetation also help to enhance chemical weathering. So once material is weathered, then it has to be eroded, and erosion is the movement of weathered material from the site of weathering. So it gets weathered, it gets broken down into smaller pieces, and then something moves those smaller pieces from the site. Typically gravity, wind, and water are what cause that to happen. So erosion is the transportation of smaller and smaller materials of weathered rock. So weathered material is eroded away from the original rock and then transported. After deposition, the material is buried, and if it's buried deep enough, it will undergo compaction, where it's squished together, and eventually lithification, which is simply the cementation, the compaction and or cementation into sedimentary rock. And limestones and sandstones and shales are all examples of those sedimentary rocks. So this is an example of the sediment cycle. You have uplift of some perhaps metamorphic or certainly igneous rock, and that uplifted material is exposed to the surface where it is weathered, and then erosion moves it away from the weathered parent material. Transportation moves it downslope by gravity. Perhaps water is involved, and eventually it's deposited out on the continental margin somewhere, or maybe even out in the abyssal plain, and as a layer upon layer is deposited, eventually you may get sedimentary rock that forms, and then as lithospheric plates collide, that lithospheric plate where the new sedimentary rock is formed is subducted underneath the continental plate, where once again you may get some melting and some uplift, and the whole process continues. And this is another basically example of the same thing, illustration of the same thing. Weathering at the top of the mountain, the rock is eroded away, the material is eroded away, it's transported downhill and then out into the ocean, where eventually the sediment is buried. Burial and compaction results in sedimentary rock. Now that sedimentary rock may be turned into metamorphic rock or igneous rock, or maybe even extrusive igneous rock, which cools at the surface. But at any rate, in some process, what used to be sediment gets turned into sedimentary rock, and eventually it gets uplifted as a mountain again, where it once again is eroded. Again, that is the sediment cycle, and specifically terrigenous sediment that comes from land. All right, the sediment of the continental shelves is called neritic sediment and contains mostly terrigenous material. Neritic refers to the continental margins. Sand and larger particles settle along the coast, while clays and silts move into deeper water. Remember, as the water slows down as it moves off the continent, the larger particles are going to fall out first. So first you're going to have sand and larger particles falling out along the coastline. The clays and the silts will stay suspended in the water as it moves into deeper and deeper water, and that's where those particles are eventually deposited. So thick layers of neritic sediment can undergo lithification, transformation into sedimentary rock, by compaction and cementation, and this rock can then ultimately be uplifted. And the Colorado Plateau is an excellent example of that. That region of North America over geologic time on several occasions was under a shallow sea, where neritic terrigenous sediment was compacted and lithified into rock, and then at a later date the entire Colorado Plateau was uplifted and exposed, which is essentially how we got the Grand Canyon. So sediment on the slope, rise, and deep ocean floor is known as pelagic or pelagic, depending on who's saying it. So it's pelagic sediments and contain a greater proportion of biogenous material. Pelagic refers to the water above the deep ocean basin. So if you remember from Finding Nemo, they talked about pelagic sea creatures and neritic sea creatures. So pelagic sediments can become lithified and uplifted as well. And a really good example of that are the White Cliffs of Dover. The White Cliffs of Dover along the southern edge of the United Kingdom, of Britain, England, these massive white cliffs. And they are essentially the skeletons of plankton, tiny plankton, that accumulated on the seafloor over millions of years, that were compacted into a sedimentary rock, which is chalk. It's literally a sedimentary rock. All that chalk is just little tiny skeletons of sea creatures, and some type of uplift there pushed that up above the water's edge, and they became the White Cliffs of Dover. And here we have thickness in meters of the sediments, and you can see where the sediment is thickest is where you get a lot of runoff off the continents, such as in the Indian Ocean, where you get all the runoff off the Tibetan Plateau and comes down to the big rivers here and feeds just a tremendous amount of sediment. We also have a lot of sediment in the Gulf of Mexico, because the rivers, the Rio Grande, and mostly really the Mississippi River, that brings sediment. And then the Amazon brings sediment, and the Congo brings sediment. But where you get a lot of sediment coming off the continent, that's where your sediments are thickest on the ocean floor. Then out in the deep ocean, that's where they're thinnest. And again, you can see that mid-ocean ridge where new oceanic crust is constantly being formed. That is where our sediments are the thinnest. And this line of blue basically follows those oceanic ridges, even over here, the East Pacific rise, and that's where your sediments tend to be the thinnest. So the general pattern of sediment on the ocean floor, you can see the dominance of oozes at high latitudes, and basically different pelagic environments support different types of biogenous sediment and you get different types of sediments on the seafloor. And of course, those areas that I pointed out as well, these are land-derived sediments. You're going to see that mainly where you have big rivers flowing out into the oceans, and you can get a lot of land-derived. And then you get out into the middle of the ocean, you start getting these pelagic sediments, clays and oozes. And then at higher latitudes, you're going to get these silicate-derived types of oozes. And it basically is just the marine environment is going to dictate the type of sediment that you can find in different locations and the thickness of that sediment as well. All right, pelagic sediments, turbidites are layers of sediment that are deposited by turbidity currents. We talked about turbidity currents earlier, where a lot of sediment gets mixed up into the water column, making that area of water more dense, and so it tends to flow downhill where it's deposited at deeper areas. These oozes are sediments that contain at least 30% biogenous material. So you have the silicate oozes that are formed by organisms that contain a lot of silica in their shells. Diatoms are one of those organisms whose remains contribute to silicate oozes. And then calcium oozes are formed by organisms that have a lot of calcium carbonate in their shells. So different types of oozes based on the different types of sea creatures that die and fall to the bottom of the sea floor, and the different types of sea creatures essentially based on the different ocean environment. So hydrogenous sediments, they originate from chemical reactions that occur in existing sediment. So they're often found in the forms of nodules, just little balls containing manganese or iron, they just sort of line around the ocean floor sometimes. Manganese nodules often form around nuclei, so something has to be there for the manganese to sort of form onto. So something like a shark's tooth lying on the bottom of the ocean may cause manganese to form around it, and you get these little nodules. Evaporites, it's a completely different thing, but it's basically the same process. The manganese and the iron precipitate out of the water. Well, evaporites are solids that precipitate out of water as the water evaporates. So that's why they're an evaporite. So you have a shallow ocean that for some changes in the climate over long periods of time, that shallow ocean or shallow sea begins to evaporate. The salts precipitate out as the water evaporates, and they just sort of are left in the bottom of what was the sea floor. So you can have salts and gypsum and a few other types that usually have some economic importance. And oolite sands form when calcium carbonate precipitates in warm seawaters in the water around the Bahama Bank. So the sand is literally not sand like silicon, but it's sand made up of calcium carbonate. We find that the white sands around the Bahama Bank. So we talked about turbidity currents, and again, the turbidity currents move quickly down the continental shelf, propelled by gravity, because the water is more dense, because it contains a lot of different sediments in it. And when the material comes to rest, it tends to sort itself into layers, with the coarser sediment falling out first. So the coarser sediment is going to be at the bottom and the finer sediment's on top. And each graded layer is the result of one turbidity current. So we'll get these different layers with coarse to fine, then coarse to fine, then coarse to fine. You see that in the very bottom illustration. And one turbidity current sends down one layer, the second turbidity current much later sends down the second layer, and that gives us an idea of what had happened in that region. All right, so here are the oozes, sometimes called marine snow. The dashed line shows the calcium carbonate compensation depth, the CCD. At this depth, usually about 4,500 meters, the rate at which calcium sediments accumulates equals the rate at which the calcium carbonate dissolves. So things dissolve more readily in the colder water. So below this line, the calcium carbonate dissolves readily in the seawater, so you don't get any oozes that form. Above that line, the calcium carbonate doesn't dissolve in the seawater as well, so you get an accumulation, and you get those marine snows. And below the CCD, water holds more CO2 because gases dissolve more easily in colder water, and that results in more carbonic acid, which dissolves the calcium carbonate faster. So above that 4,500 meter line, there's less CO2 in the water, which means there's less carbonic acid in the water, which means the calcium carbonate, the calcium shells, they don't dissolve, and they rain down on the seafloor as a marine snow. So what can we learn by studying sediment? Historical information, the location of natural resources like oil and natural gas. Marine sediments are important as historical records and the site of natural resources. Scientists can study marine sediments using many different methods, including just simply taking core samples, where they just dig down deep and get a core sample. And taking a look at that core sample with depth will give us an idea of what has happened historically back in time in that marine environment. So some of the ways, of course, scientists get their observations. They have cameras and clamshell samplers and cores and seismic profiles, and there's just lots of ways they can get information out of the sediment. So this is one method. That's the clamshell sampler. Just reaches in and scoops up a big scoop of sediment to take back and study. And then here is a method by which they get cores. And again, you can see that it lands on the seafloor and it digs down. And each subsequent layer of sediment, as you get deeper and deeper beneath the seafloor, came from a period longer and longer ago. And so this is one of the ways that we're able to sample what's happening on the seafloor and know what happened historically. So this is one method of obtaining core samples. It's called a piston core. The core allows a cylinder of sediment to be taken for analysis to determine the age of the material, as well as the density, strength, and molecular composition of the radioactivity in the sediment. So you pull the sediment up, you radioactively age it, and then you know what was happening in the marine environment above that area based on the type of sediment it is. And it's a very, very good way to get a climate history, whether it was cold or warm in the past. All right, we talked about the mid-ocean ridge in the Pacific Ocean being displaced well to the east. And so the youngest rocks in the Pacific are along that mid-ocean ridge, which basically comes from the Baja of California south into the southern Pacific Ocean. And that's where the youngest rocks are, where it says present location of the East Pacific Rise right here. So this is the East Pacific Rise right in here. And everything as you go away gets older. A stripe of rocks from the Miocene between 12 million and 26 million years ago on the west of it and on the east of it. And then a stripe of rock from the Oligocene, which would be 26 to 36 million years. And these stripes are moving away as new seafloor is formed. And then you get older and older. So late Cretaceous. So this is about the time when the dinosaurs were caused to become extinct, very likely from a comet or an asteroid that struck the Earth, probably a comet, but could have been a really big asteroid. So what that means is that 65 million years ago, this stripe of rock was being formed along the East Pacific Rise and then moving away. And it gets older and older and older, and where we start to see a change in the age is where the Pacific plate begins to subduct under other plates. And this is one of those subduction zones where we get these deep trenches. And this is another subduction zone. And at this subduction zone, the Pacific plate is moving underneath this the plate to the north, and so the Pacific plate's moving like this, and this is the subduction zone here. And so on the backside of the subduction zone, the plate goes under. Again, that's the younger plate. This is the older plate going down, and so this is the direction we're talking about. And the melting of this magma wedge is where you get volcanoes that form. And so as this plate subducts down, volcanoes form the Aleutian island chain here, the same way they formed these island chains here as this subduction was occurring. But the current day subduction is happening here, and these trenches here are this feature that gets formed when plates subduct. One subducts under the other. And so again, the explanation for all these geologic features basically always comes from plate tectonics. Again, plate tectonics, a big part of the story, not only in oceanography, but also in all geography and really the history of the world as well. So we're going to continue with our conversation about the ocean and oceanography coming up in your next lecture.